Hi and welcome to my tutorial about invertible networks for EEG decoding. And first of all, I will be presenting a Jupyter notebook, and you can follow along under this URL, so there you can also execute all the code that I will be presenting here. And as I said, I will be talking about invertible networks for EEG decoding, and I will start first with explaining the difference between discriminative and generative methods, and specifically also what generative methods can give you that discriminative methods cannot. And then looking a bit more at one such generative method, namely invertible networks, and what you can learn or what kind of insights you can gain when you apply these invertible networks to your EEG signal, and what you can learn basically about the EEG signal that you apply it to. So let's start with the distinction between discriminative and generative models as just a background. And discriminative models such as, let's say, logistic regression or a neural network that you train on a classification task, they typically give you the probability for each possible input point over the different classes. So here we have some toy example with one class in blue, class 0, and another class 1 in orange. And then this discriminative model, after it's trained, it should always tell you for any point what's the likelihood that this point comes from the orange class or from the blue class. And you could visualize it like that, where you see, okay, here it will be quite certain it's the orange class for any point, here it will be quite certain it's the blue class, and on the boundaries it will be less certain. And now a generative method will learn a bit more. It will learn the joint density between any possible input class, or for any possible input class, and for any possible input point. So for the blue class, you will see that the probability density of that class is kind of clustered in this region, and for the orange class it's a bit more spread out and in a different location. And now if you combine these two, you can also get a classifier out of it, so you can also make the prediction of the likelihood of each class given a specific input point. But you can also know a bit more, because you can know, for example, that in this region here, actually it's a very low density region for both classes, so it's unlikely to see samples from this region in general. But this is not the only thing. We'll also see some further advantages that specifically invertible networks give you, and that you can gain from them when you apply them to EEG. And the first thing we'll do now is we will use a simplified EEG example to illustrate just how these invertible networks work, so that you get a feeling for them. And this simplified example will be using the alpha power from 2 electrodes only to distinguish between the right hand movement and the resting state EEG signal. And for that we will load the so-called high gamma dataset, which is dataset we collected here in Freiburg, as I said, with different movements: right hand movement, left hand movement, resting state. And we will use the open source library BrainDecode to load this data. And what we will do, we will first load it and just select C3 and C4, because we know that these sensors are very informative about resting state versus right hand. And we will also resample to just 32 Hertz to just process all the data quite quickly. After we have done that, we will also split the data, because there's a training set here and a test set, and we will just use the training set and also split that further into a training and a validation set. And then we will extract the alpha power by just squaring the values and taking their mean over time. So we'll always have a mean squared value for each of these 4-second trials for both C3 and C4. And also in the pre-processing, to get the alpha, what we do is we use a bandpass filter here between 7 and 14 Hertz. So only the alpha range will be included in the signal, and that's why this squaring and meaning will basically give you the alpha power. Now if we plot the distribution just in a 2D space of this training data just after this manual data analysis, we already see that the resting state has much higher alpha power on both electrodes actually compared to the right hand. And now we want to learn the underlying distribution of these training data points using our invertible network. And how will it work? Here it's kind of a bit sketched. Basically what the invertible network will try to do is it will try to use the input data, learn some invertible, so bijective transformation, where in the output or latent space the data follows a prior distribution. In this case, we specified that we want two Gaussian distributions, one for the blue class, one for the orange class. So the invertible network will try to move all of these points such that they follow roughly Gaussian distributions for both classes. And how does this work? So we already said that we need invertible transformations. So for invertible networks, you try to design transformations that are invertible, exactly invertible by design. And one such transformation or one such invertible block is the so-called coupling block, which is very often used in many invertible networks. And this one works by first splitting the dimensions. So here, for example, for any point x, you of course have x1 and x2. And then you use one half of these dimensions or one part of these dimensions to compute some coefficients, in this case affine coefficients, to transform the other dimensions. So if you use the x2, you will have some arbitrary function f, which will be some neural network, and some arbitrary function g, another neural network, which you apply to the x2 to get both the multiplication factor and the addition that you will apply to x2, so some affine coefficients. And then, that you will apply to x1. And then after you have transformed x1 into x1 prime using these factors, you just concatenate again to get your x prime. And now what you should notice is that you have transformed x1, but you have left x2 intact. And this is what makes it invertible, because now you can still reconstruct the factors here. You can still compute f of x2, you can still compute g of x2, and therefore you can still subtract this and divide by this and get your original x1 back. So this is this idea of dimension splitting and coupling blocks to get one particular invertible transformation. And you can imagine that if you stack a lot of these transformations, you can have actually quite powerful models that can learn quite powerful transformations. But there are also further invertible transformations. The simplest one is of course just a linear projection, where if the determinant is not zero, you can also always invert that. And here I refer you to some blog articles which will discuss these and other transformations, because here we can only like briefly touch upon all of these workings in the invertible network, because we also want to look a little bit in what they do on the EEG signal. And the final link here also is one very popular architecture for invertible networks called GLOW that our models are also a bit inspired by. Okay, so that's basic idea of these invertible networks, to always transform to this prior distribution with some bijective invertible transformation. And yeah, so we will first create such a network. Here you see this infermute is basically this linear projection which doesn't have determinant of zero, so you can invert it. And then you have these coupling blocks, which I have explained just now. And you can stack several of these kind of sequences, and then you have a fairly powerful model. Again, if you want to know more details, then look at these block links above. And now we will train it, and how the training works, again, we can only briefly touch upon it here, but basically, now since you have some invertible transformation, you are able to always compute exactly the likelihood of each data point. Why? Because once you have transformed it to the output, you can evaluate the likelihood under your priors. So here I can always compute, if I have imagine some Gaussian distribution here, I can always compute the likelihood of, or the density of each point under this Gaussian distribution, and the same also for the other Gaussian distribution and the blue points. And then I can just try basically to move all points to the highest density. But since we are a bijective network, we can't just collapse everything to a single point, and that's why you still get like a valid probability distribution in the end. There are some like technical details about this, where basically you have to account for how much you squeeze and expand the volume here of these points. But basically you can also look that up in these articles, how it exactly works mathematically. What you need to know here now only is that, okay, you try to basically squeeze all these points more and more into the high density regions of your prior, and at the same time you can't just collapse them because you have invertible transformation. So we do that now, and then after we've trained our network, of course we want to have some idea how good it is. The first thing we can do is we can just generate samples. So we can just ask our network now, okay, please generate some samples from the two distributions that you've learned. And that's what we see here. And now I would claim that this looks actually pretty good. It looks pretty similar to the original data. So if you remember the original data was here, I would say, okay, it has learned some reasonable distribution from the training data. You can also, since we are now in a 2D case, you can also do it even more explicitly. You can create a grid and plot the probability distributions. So here you have the right-hand distribution, and here you have the resting state distribution. And yeah, you can basically also see it has learned something reasonable. Here very clustered, here a bit more spread. And also at the same time, you can transform these two, as we also saw in the very beginning, to get a classifier again. Yeah, because you can always look at each point, which of these densities is higher and how much, and then you get your class probabilities for each input point. Finally, what I showed in the beginning of this section, you can also, I will show it here again, is the transformation. You can, of course, for this 2D example, you can look at where does each input point get mapped to in the output point, just to have a bit better understanding what the network has done. And that's what these very thin lines show here. You can also just evaluate how good it works as a classifier, and here we get about 92% for the training accuracy and about 82% for the validation accuracy. Okay, so that was interesting, but now we will go to the raw data or the time series data. Yeah, it will still be a bit simplified, just 32 Hertz, 2-second windows. We'll only use C3 now, only a single electrode, and we will still stay in the alpha band. But basically the aim will now be to see if we can still understand a little bit what are the differences between the classes that this network has learned. So now, yeah, the pre-processing is stay roughly the same, except we only take one electrode now, just to have some quick examples in this tutorial. And yeah, we again take train and validation set, and the model looks a bit different now because we need a convolutional model now, or we want to use a convolutional model, and we'll have 1D convolution since we only have the time dimension here. And yeah, the basic ideas are still the same. So you still have these coupling blocks, you still have these linear projections, and so on. Yeah, and as I said before, you can also look at the glow model to understand a bit better the individual blocks that we are using here. Okay, so now we have a kind of different network, but we can still train it in the same way using the maximum likelihood training. And this is what we will do here for 2000 epochs. Since this takes quite some time, I've also supplied already some pre-trained models that we can just load that were like reached after these 2000 epochs. And the first thing we can just look at again is these accuracies. We can also look at the negative log likelihood, which will give us some idea about how well it has learned the density, but this is a bit harder to interpret here. So we'll look a bit deeper just into the accuracies, and we see it's quite good now. It has like 94% and on the training and 93% on the validation set. And now, as I said, what we now would like to see is, can we understand a little bit what are the differences between the classes that it has learned. Here for this example, of course, we have a clear idea what it should learn because we know that the alpha power is different. And indeed, if we try to understand this network, we also see that. What we'll do now is, you can basically imagine in the 2D space before, you have some like maximum of your Gaussians in the output space here and here, and you can look where these maxima are in the input space. Of course, for this 2D example, that would be not so interesting. It might be somewhere here and somewhere here. But now for this data in the time domain, where you have already like 64 dimensions because you have 64 time steps, it becomes a bit more interesting. Basically, when you look at that, here is the difference in the output space. There already you see something a bit strange. So just in the output space, you see this is the orange line is for the resting state learned distribution mode. So this is the most likely resting state output point. And the blue one is the most likely right-hand point in the output space. And the green is basically something neutral in between the two classes that would have equal probability for both classes. Now you see here something a bit strange, that the first 32 dimensions, there are always these differences, and then everything becomes much smaller and they're much more similar. And there's a reason for that, namely that in this network we introduced a special block at the end, which we found very helpful for EEG decoding. What this one does is it transforms, basically it takes these 32 first dimensions, uses them as some kind of x coordinate, the 32 next dimensions uses them as some kind of y coordinate, and transforms to polar coordinates. So basically something where you have a notion of a length of a vector or an amplitude, and the notion of an angle or a phase. And we found this kind of transformation, which is also completely invertible, to be quite helpful for EEG to get more interpretable EEG decoding models that can more easily learn amplitude-based or amplitude-like features. Of course, it may still learn anything it wants before, so you can't interpret it very easily, but we've just seen it becomes a bit more clear what it's doing often, so that's why we use this special block here. Yeah, so that's why we have these differences mostly in the first 32 dimensions, because these are basically the amplitude dimensions and the next ones are the phase dimensions. So you can already see that it seems most of the differences in the amplitude dimensions, as one would also expect for this kind of task. But then, more interestingly also, you can go back. You can take, for example, the resting state point in the output space, the most likely resting point output, and go back to see the most likely resting point input, resting state input. And then what you see when you compare it to the most likely right-hand input, you see exactly what you would expect, these higher amplitudes, right? The orange one is always a bit higher in the amplitude compared to the blue one, and the green one, like the neutral one, is in between. So that's kind of a neat way or a simple way to kind of some understanding of the most basic differences that the network has found here. And now we'll go one step further and basically do everything exactly the same way. Just we will remove this bandpass filter, because then it's a bit less clear what the network might use or might not use. And also we will try now to go a bit deeper into individual inputs and see what the network does on individual inputs. But okay, first we'll just do the pre-processing, but now without any bandpass filter. We again split into training and validation and so on. The network stays exactly the same in its structure, and also the training is exactly the same. And the first thing, of course, we can do is again look at the accuracies. And we see before we had 92.9%, now we have 92.0%. So there is some difference, but the difference is quite small, especially if you consider during the training, sometimes these values will fluctuate quite a lot. So it even went up here to above 96%. So I would claim it has stayed roughly the same, only become like a little bit worse, but kind of stayed roughly the same in terms of validation accuracy. Yeah, now we can again visualize these most likely inputs for each class. And now you see something a bit different. In the output space it actually looks very similar, but if you look in the input space, you can see that now, okay, you still have these amplitudes that are higher for the resting state when you compare the orange to the blue line. But at the same time you also see that the very lower frequency plays some role, because over these are 2 seconds, yeah, it's 32 Hertz, 2 seconds. Over these 2 seconds, the resting state signal starts much higher, or the most likely resting state signal starts much higher and ends much lower compared to the right-hand signal. So that's interesting. And then one thing we thought about was, can we look at individual examples, especially individual examples, individual inputs that were predicted wrongly, and try to get at least an idea of what might go wrong there in the network, or what causes the mistake basically. Can we have some, just gain some ideas that we can investigate then further with some manual analysis. And this is, yeah, something we will do now. And this is a bit more involved, so I'll try to go step by step through it. What we do here, what our aim is, we will try for any given input, we will try to basically decompose it into parts that are indicating class A and parts that are indicating class B. So parts that are indicating the resting state class and parts that are indicating the right-hand class. And how we will do it here is we will first push the input signal through our invertible network to the output or latent space, and then we'll get this black output here, for example, for one specific input example. So we'll have this black output example here, and now we plot alongside also the two means of the class distributions. So the orange one is the mean of the class distribution for the resting state, and the blue one is the mean of the class distribution for the right-hand signal, for the right-hand class. And what you can see here is that actually for some dimensions, remember all of these dimensions are now independent, so we have Gaussian distributions which are independent in each dimension as our prior. And you can see that some of these dimensions, the input seems to be more likely under the resting state class, like for example here, it's more, it's above the orange parts, and the orange parts are above the blue parts. But here, for example, actually this dimension or also this one, it seems that actually in these dimensions the right-hand class is more likely than the resting state. So now what we're trying to do is, can we somehow visualize these different components within one signal that are indicating the different classes? And so here you can also see this plotted a bit differently, where we just show like the relative probability of each class for each dimension. So you can see that, and here for the correct class, which is, I think, in that case, might be resting state or right hand. Actually, I don't remember clearly now, but I think, yeah, could be resting state. Yeah, should be resting state, the correct class here. And then you can see, yeah, as I said, some dimensions actually are indicating the correct class quite strongly, others are actually indicating the incorrect class. And now what we'd like to do is, yeah, decompose the signal into two parts for class A and class B. And what we can do is, well, we just use each dimension and we check, is the dimension, let's say, indicating the resting state, the orange stuff, or is it indicating the right hand? So here we have color coded it already. We have taken this black line and color coded each point according to which class it indicates. And then we can say, okay, if we want to know the signal parts which are indicating the resting state, then we can just reset all of these blue points to the neutral point in between. So this green line again is the neutral neutral points in between the two classes. So for each dimension here, the green point will have equal likelihood under both classes. So if we just reset here all of these blue points to the green line, then actually in theory only the parts of the signal that indicate the resting state should remain in the signal, and everything else should be reset to some default value in a sense. And if we do that, we can do it also the other way around, reset all the orange points and only keep the blue ones, and then we get two different signals. And this is what you see here in the input space after inversion. And also we plot the green one, which will always be the same because that's independent of the input, it's just a neutral mean. And also in black you also see the original signal. And now what you can try to learn here is you can just visually try to see, of course it's not easy because it's a learned decomposition, so you don't really know what to exactly look for, but you can try to see if you can spot some identifiable parts where the orange one seems to be more consistent with the original black one, or where the blue one seems to be more consistent with the original black one. And I would claim here that you can see in this alpha range, especially in this later part of the signal, where the original signal has a higher amplitude, of course the orange one is more consistent also with its higher amplitude. But if you look at the low frequency or the overall trend in the signal, actually the blue part, which indicates the right hand signal part, is more consistent with the signal. As you see that the blue part follows more this black line than the orange part, especially in the beginning. And that's all kind of makes sense. It's consistent with what we've seen before, because before we saw that you should expect that the resting state should start high and end low, and in this signal we don't really see that, right? Okay, but now we can also look at these signals with more examples, or this method with more examples. And here, yeah, we have both right-hand signals and resting state signals, and we will now focus a little bit. So here we'll always see original signal, what indicates the right, what indicates the rest, together with the neutral signal, which is always the same, and then the overlaid plot, which we've seen just now. And we'll focus now on the ones where the network made mistakes. So you see 2 times here it made wrong predictions. Here it was always correct, but here it made some wrong predictions. And the first thing you can see for the first wrong prediction, so here it has predicted resting state instead of right hand. And you see, it seems, if you look at the resting state signal component, there are some higher amplitudes, especially in the later parts of the signal. Yeah, and that's for the first example. And for the second example, what you can see is here it doesn't seem to be so much about alpha, right? This resting state signal component, but rather about a frequency a bit lower. If you see the shape here. And we'll now try to basically, this is just ideas that we can gain from this visualization, and now we're try to manually investigate them further. So yeah, here we have this signal again that was mispredicted with the 4 stuff, the original signal and the right hand component and the resting state component and the neutral one. And now the hypothesis was that, okay, it seems that more in the later part of the signal, the amplitude is very high for this resting state component, so maybe this later part of the signal is the problem. And we can try to verify that by just saying, okay, what would happen if we only take from the second half of the signal, take that and scale it down. Basically, we'll leave the first part intact of the black line, but the second part of the black line, we will scale it down a little bit and see what happens. And indeed, if we do that here, so in black it's the original signal, in violet pink it's the manipulated one where we scaled it down just a little bit in the second half, the prediction is corrected again. So for the original one it was only giving about 8% probability to the correct class, but which is in this case the right hand class. But after this correction or after this manipulation of the input signal, we see that actually now it's above 50% at about 61%, predicting the right hand, the correct class. And now, yeah, so we see here, okay, that kind of seems to be correct, that, okay, it's enough to just scale down the later part a little bit and then you get a correct prediction. And now we can also look at the second example where we had a different idea, where we said, okay, it seems that somehow these a bit lower frequencies here in this resting state seem to be a problem, resting state component. And we can also check that, because we can just do now a Fourier transformation of the original signal of the black one, and just set the all the signal components below 6 Hertz, scale them down really a lot. And then what it looks like is this. You see here again in black the original signal, and then in pink violet the manipulated one, and you see that kind of this alpha peaks are not really changed, they're just shifted, but the size is roughly the same. But these low frequencies are removed. And then you can also see before this manipulation it just predicted with 19% the correct class, which is again the right hand. But after this manipulation the correct prediction increased to 55%, so now it would actually make the correct prediction overall. Yeah, so these are like some things you can do with these invertible networks, and of course you can also use much more complex data with many sensors and longer times and so on. You'll just have to run it longer. And yeah, I've supplied you all the code here so you can play around with it and yeah, see what you would get on your own data. And also yeah, you can feel free to just contact me if you have any further questions about these invertible networks on the EEG data. Thank you very much for listening to my tutorial.